Standard integrals of rational functions, non-radical. Okay, so we're starting a new section on integrating rational functions. Specifically, we're going to look at some standard integrals. That is, integrals that appear so often, it's worth memorizing the results. This slide introduces the scope of what we'll be covering. We'll be exploring 3 fundamental integration formulas. Now, these aren't just any integrals. They deal with integrals where the thing we're integrating, the integrand, is a rational function, and the denominator of that rational function involves a quadratic expression. Think of a quadratic expression as something like ax squared plus bx plus c. So, the integrals we'll be tackling will have a fraction where the bottom part, the denominator, is a quadratic. The key thing to understand is that these formulas are essential tools in calculus. They allow us to solve certain integration problems very efficiently. Instead of having to go through a potentially long and complicated derivation every time, we can simply plug in the values and get the answer. We'll be seeing how these formulas are derived using techniques like partial fractions and trigonometric substitution in the following slides. But for now, the focus is on recognizing when to apply these formulas. In the next few slides, we'll break down each of these 3 formulas, show you how they're derived, and work through some examples so you can get comfortable using them. So, let's get started with the first one, which deals with the difference of squares. 1. The difference of squares, variable first. Now, let's dive into the first specific formula. This slide focuses on the case where we have an integral of 1 over x squared minus a squared. The formula is as follows. The integral of 1 over x squared minus a squared with respect to x is equal to 1 over 2 a times the natural logarithm of the absolute value of x minus a divided by x plus a plus the constant of integration, c. Let's break down how we arrive at this formula. We're going to use a technique called partial fractions. Step 1. Factorize the denominator. The first thing we do is factorize the denominator, x squared minus a squared. Remember from your algebra, this is a difference of squares. It factors nicely into x minus a multiplied by x plus a. So, our integral now looks like the integral of 1 over the product of x minus a and x plus a. Step 2. Express as partial fractions. Now comes the core of the partial fraction decomposition. We assume that we can rewrite the fraction 1 over x minus a times x plus a as the sum of 2 simpler fractions, a over x minus a plus b over x plus a. A and b are constants that we need to determine. To get rid of the denominators, we multiply both sides of the equation by the original denominator, which is x minus a times x plus a. This gives us 1 equals a times x plus a plus b times x minus a. This is a crucial step, as it transforms our integral into an algebraic equation that we can solve for a and b. We'll do that on the next slide. Okay, so we've established that we're looking at standard integrals of rational functions. Specifically, those where the denominator is a quadratic expression, and importantly, doesn't involve any square roots. We've already discussed why these standard integrals are useful. They save us time and effort by giving us a direct result, rather than having to perform a full integration from first principles every time. Derivation of difference of squares, variable first, continued. Okay, so we're continuing with the derivation of the integral of 1 over x squared minus a squared using partial fractions. Now, let's move on to step 3, where we solve for the constants a and b. Remember from the previous slide, we arrived at the equation 1 equals a times x plus a plus b times x minus a. To find a, we'll use a clever trick. We'll substitute a value for x that eliminates b, so let's set x equal to a. If we substitute x equals a into our equation, we get 1 equals a times a plus b times a minus a. This simplifies to 1 equals a times 2a, or 2a. Solving for a, we divide both sides by 2a, giving us a equals 1 over 2a. Now, to find b, we'll do the same thing, but this time we'll substitute x equals negative a. This gives us 1 equals a times negative a plus b times negative a minus a. This simplifies to 1 equals b times negative 2a, or negative 2ab. Solving for b, we divide both sides by negative 2a, which gives us b equals negative 1 over 2a. Great, we've now found the values of both a and b. Let's move on to step 4, where we integrate the decomposed fractions. We had previously expressed 1 over x squared minus a squared as the sum of two fractions, 1 over 2 a times x minus a plus 1 over 2 a times x plus a. Now we can integrate each of these terms separately. So, the integral of 1 over x squared minus a squared dx is equal to the integral of 1 over 2 a times x minus a dx, minus the integral of 1 over 2 a times x plus a dx. Notice that 1 over 2 is a constant, so we can pull it out of both integrals. The integral of 1 over x minus a dx is the natural logarithm of the absolute value of x minus a. Similarly, the integral of 1 over x plus a dx is the natural logarithm of the absolute value of x plus a. Don't forget to include the constant of integration, c, at the end. So, we have 1 over 2 a times the natural logarithm of the absolute value of x minus a minus 1 over 2 a times the natural logarithm of the absolute value of x plus a plus c. Finally, in step 5, we'll use a logarithmic property to simplify this expression. Remember the property that the logarithm of m minus the logarithm of n is equal to the logarithm of m divided by n. Applying this property, we can combine the two logarithmic terms into a single logarithm. The natural logarithm of the absolute value of x minus a divided by the absolute value of x plus a. This gives us our final result, 1 over 2 a times the natural logarithm of the absolute value of x minus a divided by x plus a plus c. And that completes the derivation of this standard integral. This formula is really useful, and we'll see how to apply it with an example on the next slide. Remember, understanding the derivation helps you remember the formula and apply it correctly. Example for difference of squares, variable first. Okay, let's work through an example to solidify our understanding of the first standard integral we discussed, the one involving the difference of squares. We're asked to evaluate the indefinite integral of 1 over x squared minus 9 with respect to x. Now, step 1 is to identify the constant a in our formula. Remember, our formula is integral of 1 over x squared minus a squared dx equals 1 over 2 a times the natural logarithm of the absolute value of x minus a over x plus a, plus the constant of integration, c. Looking at our integral, we can rewrite x squared minus 9 as x squared minus 3 squared. This makes it clear that a is equal to 3. Now for step 2, we simply apply the formula we just reviewed. We substitute a with 3 in our formula. So we have 1 over 2 times 3, which is 1 over 6, multiplied by the natural logarithm of the absolute value of x minus 3 over x plus 3. And don't forget to add our constant of integration, c. Therefore, the integral of 1 over x squared minus 9 dx is equal to 1/6 times the natural logarithm of the absolute value of x minus 3 over x plus 3 plus c. This example demonstrates how straightforward applying the formula can be once you've correctly identified the value of a. In the next slides, we'll explore a similar process for the case where the constant term comes first in the denominator, and then we'll move on to integrals involving the sum of squares. To the difference of squares, constant first. Here on slide 5, we have the formula for the integral of 1 over a squared minus x squared. This is written as the integral of dx over a squared minus x squared equals 1 over 2 a times the natural logarithm of the absolute value of a plus x divided by a minus x plus the constant of integration, c. Now let's break down how we arrive at this formula, and as before, we'll use the method of partial fractions. Step 1, factorize the denominator. The first thing we do is factorize the denominator, a squared minus x squared. Remember from your algebra, this is a difference of squares, so it factors nicely into a minus x multiplied by a plus x. Therefore, 1 over a squared minus x squared is the same as 1 over the product of a minus x and a plus x. Step 2, express as partial fractions. Next, we express this fraction as a sum of simpler fractions using partial fractions. We assume that we can write 1 over a minus x times a plus x as a over a minus x plus b over a plus x. To get rid of the denominators, we multiply both sides of the equation by the original denominator, which is a minus x times a plus x. This gives us 1 equals a times a plus x plus b times a minus x. This is a crucial step, as it allows us to solve for the unknown constants, r and b. Okay, so let's move on to our second case for integrating rational functions. As we saw in the previous slides, we're focusing on integrals where the denominator is a quadratic expression, but doesn't involve any square roots. Now, we're going to look at a scenario where the constant term appears first in the difference of squares. We'll continue solving for a and b and completing the integration in the next slides. Remember, the key here is to systematically break down the complex integral into simpler parts that we can easily handle. Derivation of difference of squares, constant first, continued. Now let's move on to step 3, where we solve for the constants a and b. Remember, we set up our partial fraction decomposition earlier. We're going to use a clever trick here. To find a, we substitute x equals a into the equation, 1 equals a times a plus x, plus b times a minus x. So, if x is a, we get 1 equals a times a plus b times a minus a. This simplifies to 1 equals a times 2a, and therefore, solving for a, we find that a equals 1 over 2a. Now, to find b, we do a similar thing, but this time we substitute x equals negative a. So, we have 1 equals a times a plus negative a plus b times a minus negative a. This simplifies to 1 equals b times 2a, and solving for b, we get b equals 1 over 2a. Notice that in this case, a and b are equal. Alright, now we move on to step 4, where we actually integrate. We've broken down our original integral into 2 simpler integrals. So, the integral of 1 over a squared minus x squared dx is equal to 1 over 2a times the integral of dx over a minus x, plus 1 over 2a times the integral of dx over a plus x. The integral of dx over a minus x is negative log of the absolute value of a minus x. And the integral of dx over a plus x is log of the absolute value of a plus x. Don't forget the constant of integration, c, at the end. Finally, in step 5, we simplify using logarithmic properties. Remember that log m minus log n is equal to log of m over n, so we can rewrite our expression as 1 over 2a times the quantity log of the absolute value of a plus x minus log of the absolute value of a minus x. Plus c, this simplifies further to 1 over 2a times log of the absolute value of a plus x over a minus x plus c. Okay, so we're continuing the derivation for the integral of 1 over a squared minus x squared. And that, my friend, is the final result for the integral of 1 over a squared minus x squared. This formula is crucial, so make sure you understand each step. In the next slide, we'll see an example of how to apply this formula to a specific problem. Example for difference of squares, constant first. Okay, let's tackle another example. This time, we're going to evaluate the integral of 1 over 25 minus x squared, written as integral of 1 over 25 minus x squared dx. Step 1, identify the constant a. Now, remember from the previous slides, we have a specific formula for integrals where the denominator is a difference of squares, but with the constant term first. We need to rewrite our integral to match that form. Notice that 25 minus x squared can be written as 5 squared minus x squared. This is crucial because it allows us to identify our constant a in this case, a is equal to 5. Step 2, apply the formula. Now that we know a equals 5, we can directly apply the formula we derived earlier for the case where we have a constant first in the difference of squares. The formula is 1 over 2a times the natural logarithm of the absolute value of a plus x divided by a minus x, plus the constant of integration. See, let's substitute a equals 5 into the formula. That gives us 1 over 2 times 5, which is 1 over 10, multiplied by the natural logarithm of the absolute value of 5 plus x, divided by 5 minus x, plus c. So, our final answer is 1/10 times the natural logarithm of the absolute value of x plus 5, divided by 5 minus x, plus the constant of integration, c. Remember, this formula is specifically for this type of integral, a rational function with a denominator that's a difference of squares, where the constant term comes first. In the next slides, we'll move on to a different type of integral, one involving the sum of squares and a different integration technique. 3. The sum of squares. Now, looking at this slide, we have the formula for integrating 1 over x squared plus a squared. This integral evaluates to 1 over a, multiplied by the inverse tangent of x over a, plus our constant of integration. So, mathematically, it's written as integral of 1 over x squared plus a squared dx equals 1 over a times inverse tangent of x over a plus c. Now, the derivation of this formula is a bit different from the partial fractions we used earlier. Instead, we'll employ a technique called trigonometric substitution. You'll recall from trigonometry that the identity 1 plus tangent squared of theta equals secant squared of theta is fundamental. This identity is going to be crucial in simplifying our integral. The reason we use this trigonometric substitution is because the denominator, x squared plus a squared, resembles a part of the secant squared identity. By cleverly substituting x with a trigonometric function, we can transform the integral into a form we can easily solve. We'll explore the specifics of that substitution in the following slides, but it's important to understand why we're choosing this method. It's all about recognizing the structure of the integral and applying the appropriate technique. Okay, let's move on to our third standard integral, dealing with the sum of squares. As we've seen with the difference of squares, recognizing the form of the denominator is key to choosing the right integration technique. In the next few slides, we'll walk through the steps of the substitution, simplifying the integral and ultimately arriving at this final formula. Remember, mastering these standard integrals isn't about memorization, but about understanding the underlying principles and techniques. Derivation of sum of squares, continued. Okay, so we're continuing the derivation for the integral of 1 over x squared plus a squared. Remember from the previous slides, we've tackled integrals using partial fractions, and now we're moving on to a different technique, trigonometric substitution. This is particularly useful when we have a sum of squares in the denominator, like we do here. Let's look at step 1. We're going to substitute for x. We'll let x equal a times tangent of theta. So x equals a tan theta. Now, this might seem a bit arbitrary, but trust me, it's a highly strategic move. The key is that we need to also find what dx is in terms of theta, because we're going to be changing our variable of integration. To do that, we differentiate both sides of the equation x equals a tan theta with respect to theta. The derivative of a tan theta is secant squared theta, and since L is a constant, it just comes along for the ride. So, we get dx equals a secant squared theta d theta. This is crucial. It tells us how to convert our integral from being in terms of dx to being in terms of theta. Now, let's move on to step 2. We're going to substitute both x and dx into our original integral. Our original integral was integral of 1 over x squared plus a squared dx. Replacing x with a tan theta and dx with a secant squared theta d theta, we get the integral of a secant squared theta d theta all over the quantity, a tan theta squared plus a squared. Let's simplify that denominator in step 3. Notice that both terms in the denominator have an a squared in them, so we can factor out an a squared, giving us the integral of a secant squared theta d theta all over a squared times the quantity tan squared theta plus 1. And here's where a key trigonometric identity comes in handy. Remember that tan squared theta plus 1 is equal to secant squared theta. So we can replace tan squared theta plus 1 with secant squared theta. This gives us the integral of a secant squared theta d theta all over a squared times secant squared theta. Derivation of sum of squares, continued. Okay, let's continue with the derivation of the integral of 1 over x squared plus a squared. Now, we've simplified our integral down to a very manageable form. Looking at the slide, we're now at step 4, integrate. Notice that after our substitutions and simplifications in the previous steps, we are left with the integral of 1 over a, with respect to theta, written as integral of 1 over d theta. Since a is a constant, 1 over a is also a constant. The integral of a constant is simply the constant multiplied by theta. So, the integral of 1 over a d theta is equal to 1 over a times theta, plus our constant of integration. So we have integral equals 1 over a theta plus c. Now, this is great, but our original integral was in terms of x, not theta. Therefore, we need to express our answer back in terms of x. That brings us to step 5. Convert back to x. Remember our initial substitution? We said that x equals a times the tangent of theta. From this, we can rearrange to find theta in terms of x if x equals a times the tangent of theta. Then the tangent of theta equals x over a, and if the tangent of theta equals x over a, then theta equals the inverse tangent of x over a in mathematical terms. This is written as arctangent of x over a. Now, we can substitute this back into our integrated expression. We had 1 over a times theta plus c replacing theta with the inverse tangent of x over a. We get 1 over a times the inverse tangent of x over a plus c. And there you have it. We've successfully integrated 1 over x squared plus a squared. This result, 1 over a times the inverse tangent of x over a plus c, is our standard integral. Remember this, as it's a very useful one to have in your toolkit. In the next slides, we'll look at an example to solidify our understanding, and then summarize all the key takeaways from this section. Example for sum of squares. Okay, let's tackle another example to solidify our understanding of integrating rational functions. This time, we're going to evaluate the integral of 1 over x squared plus 4 with respect to x. Now, looking at the integral, we need to identify which of our standard formulas applies. As you recall from the previous slides, we have a formula for integrals where the denominator is a sum of squares, something in the form of x squared plus a constant squared. This is exactly what we have here. Step 1. Identify the constant a. We need to rewrite our denominator, x squared plus 4, to match the form in our formula, which is x squared plus a squared. We can see that 4 is equal to 2 squared. Therefore, our constant, a, is equal to 2. Remember, a represents the square root of the constant term in the denominator. Step 2. Apply the formula. Now that we know a is 2, we can directly apply the formula we derived earlier. The formula is 1 over a times the inverse tangent of x over a, plus the constant of integration. Substituting a equals 2 into the formula, we get 1 over 2 times the inverse tangent of x over 2, plus so. The integral of 1 over x squared plus 4 with respect to x is equal to 1/2 times the inverse tangent of x over 2, plus the constant of integration. And that completes this example. Remember, recognizing the form of the denominator is key to choosing the correct formula. We'll be moving on to a summary of the key takeaways and common mistakes in the next slides, so make sure you've understood this example before we proceed. Key takeaways. Okay, let's recap what we've learned about integrating rational functions. This slide, slide 12, serves as a handy summary of the key formulas we just derived. As you can see, we have a table organizing the information. The first column, titled Form of Denominator, shows the different types of quadratic expressions we've been dealing with in the denominator of our integrals. The second column, Formula, presents the corresponding integral formula for each denominator type. Let's go through them one by one. For a denominator of x squared minus a squared, the integral evaluates to 1 over 2a, multiplied by the natural logarithm of the absolute value of x minus a divided by x plus a, plus the constant of integration. Remember, we arrived at this formula using the method of partial fractions, as we saw in slides 2 through 5. Next, if the denominator is a squared minus x squared, the integral becomes 1 over 2a, multiplied by the natural and logarithm of the absolute value of a plus x divided by a minus x. Again, plus our constant notice the slight difference in the logarithmic argument compared to the previous case. This is crucial, and we also derived this using partial fractions, as shown on slides 5 through 7. Finally, when the denominator is x squared plus a squared, which is the sum of squares, the integral is 1 over a, multiplied by the inverse tangent of x over a plus c, we obtained this result using trigonometric substitution, specifically letting x equal a times the tangent of theta, as we detailed on slides 8 through 10. The third column, method of derivation, simply reminds us which technique, partial fractions, or trigonometric substitution, we used to arrive at each formula. This table is a great reference point. When you encounter an integral with a rational function, quickly identify the form of the denominator, and then select the appropriate formula from this table. Keep in mind that in the next and final slide, we'll be discussing some common mistakes students make when applying these formulas, so pay close attention to those to avoid those pitfalls. This will help solidify your understanding and ensure you can confidently tackle these types of integration problems. Common mistakes. First, let's talk about confusing the logarithmic arguments. Remember those formulas we derived using partial fractions? Specifically, the ones involving the natural logarithm. It's really easy to mix up what goes inside the logarithm. When you have an integral resulting in a logarithm with a fraction, the order of terms in the numerator and denominator is crucial. If your denominator was x squared minus a squared, in the log, you'll have x minus a divided by x plus a. Notice the x term comes first in the numerator, but if your denominator is a squared minus x squared, then in the log, it's a plus x divided by a minus x. The constant, a, comes first in the numerator. Pay very close attention to this. It's a frequent source of errors. Next, ignoring the constant c, this is a fundamental mistake in integration. Every indefinite integral, meaning an integral without specific limits, must have a constant of integration, which we denote as c. It represents the fact that the derivative of a constant is 0, so there are infinitely many possible constant terms that could be part of the original function. Don't forget to add it. Now let's address incorrect a value. When you're identifying the value of a in these formulas, remember that a represents the square root of the constant term. For example, if you see x squared plus 16 in the denominator, it's tempting to think a is 16. But a is actually 4, because 4 squared equals 16. Always take the square root to find the correct value of a. Finally, tan inverse versus 1 over tan. This is a common confusion with trigonometric functions. The notation tan inverse of x, or arctangent of x, represents the inverse tangent function. It asks, what angle has a tangent of x? It's not the same as 1 divided by the tangent of x, which is the cotangent. Be careful not to confuse the inverse trigonometric function with its reciprocal. Okay, let's move on to the final slide, which highlights some common mistakes students make when working with these standard integrals. It's good to be aware of these before you encounter them in your problem solving, so you can avoid them. So keep these common pitfalls in mind as you practice, and you'll be well on your way to mastering these standard integrals. Remember, practice makes perfect.